Hi, how are you? Thanks for coming here directly after Tim's talk. So again, thank you. My name is Tony Hooyberghs, and today I will be talking about quantum computing. I've been doing this quantum computing talk for a couple of years now. Conferences seem to like it. The audience seems to like it. And because I'm doing it for a couple of years already, there's some evolution, of course. I try to do different things. And because of that, I want to ask, did any one of you already seen my talk in the past? Nobody. Does anyone have any idea what quantum computing is about? Okay, a couple of you, perfect. Then I suggest that I do a very quick introduction into what I think quantum computing is and how it can help us in the future. After that quick introduction, I will basically create an existing quantum algorithm by doing some live coding. So fingers crossed if I will make that work. I just chose a very simple quantum algorithm that I can use to show you how to use the language Q# to do that. And I will explain throughout me writing code and GitHub Copilot working with me on that, again, hopefully. So yeah, the reason I'm doing this talk is because in 2019 I was attending Techorama in Belgium, a conference in Belgium, and I saw a speaker doing a talk on quantum computing. And to be honest, after 1 hour, I was mind blown in the bad way. I had no idea what he was talking about. Which is basically what happens if you watch the Kardashians. But that's when I decided, okay, I'm going to try to do a better job with the emphasis on try. And I'm going to talk from one software developer to another software developer, you the audience, and I'm going to try to explain on my intelligence level to you what I think quantum computing is all about. So yeah, I am a software developer, so I have no experience in doing actual quantum stuff. I don't work on physical quantum computers. This is basically just a hobby that got a little bit out of hand. I work as a software consultant for a consultancy firm in Belgium called Involved, and I just try to have some fun and talk at conferences, and because I have some fun doing this, I also got the Microsoft MVP award, which allows me to have more fun. So please join me in this fun little session. Everything that I'm going to talk about today is already available online. So I have a GitHub repo specifically for Future Tech 2023. Everything is there, all the code samples, but also the slides. So basically you can already walk outside because you have everything available. So let's dig in. I want to start with a little story that happened to me when I was a teenager. When I was in school in Belgium, I was attending a class for technical drawing using AutoCAD. It has nothing to do with quantum computing. But I was finished early with my exercises, and the teacher knew that I was doing software development in my free time. Software development is kind of a fancy word. I was fiddling around with BASIC on an MS-DOS computer, basically. And he asked me during that lesson where I finished my exercise, I have a fun little project for you. He said there is such a thing as the knight's tour problem, where on a chessboard you have a knight's piece, and a knight's piece, as you know, can do these 8 different jumps to these 8 different positions. And the teacher asked me, could you write an algorithm that tries from a random starting position to do these horse jumps around the entire chessboard and visits each square exactly once. Can you do that? I was like, sure, I can do that. I think I was 14 years old. I had no idea about recursion, so I did 64 for loops within each other. So I did it, spent a whole lot of time programming, and I ran the application. And it ran. But it didn't come to a conclusion in seconds, what I thought computers were good in. So I waited a little bit more. I stopped. I canceled. I started debugging. I had no idea what I did wrong. I thought I was doing a good job. That was in the 90s, so after a couple of hours, I abandoned the problem and just went to play outside like every kid would do in the 90s. And I totally forgot about this. It was only later when I was older and in university that somebody told me that this is one of those exponentially large problems, that when you make the wrong jump and you are stuck, you basically need to backtrack and you need to try a different route. But if you do this and you make the wrong decisions all the time, this can take a long time for a computer even to jump through all of these paths. And I had no idea when I was a child. And today it's still hard to grasp that with only 64 squares, there are so many different possible paths that a computer can take and can actually take even hours, days, years to solve a problem if you make the wrong mistakes. So yeah, this is why we need quantum computing today. This is why we need another kind of computing than classical computers, because classical computers are still bad at solving exponentially large problems. So, why does quantum computers work? Well, they basically borrow concepts from quantum physics. So in quantum physics, we have concepts like superposition and entanglement. So superposition is a graphic that I created on the left-hand side, where a certain property of a very tiny quantum scale object can be in multiple states at the same time. That's not entirely correct. It's not multiple states at the same time. But the idea is that it basically, in this case, the spin of an electron, it can be up or it can be down, two distinct states, but it can also be, let's say, two at the same time. Now, this is interesting because with this we can do a lot of crazy stuff. The thing you need to remember is this only works on a quantum scale, so on a very tiny microscopic scale, like for example the spin property of an electron. On a macroscopic scale, it doesn't work. Like the chair you're sitting on right now, it's not a quantum object, so it also cannot be in superposition. It cannot be in superposition of underneath you and your neighbor at the same time, luckily. I always make the same joke, but the only thing on a macroscopical scale that I can think of is a USB slot. If you try to put something in, it also never works because you have no idea how it's oriented. The orientation of your classic USB A slot is also in a kind of superposition. A very weird thing about superposition is the moment you observe it, the moment you look at it, it makes that decision and it will jump to either one of its distinct states. Again, just like the USB key, you need to watch it and then you can see, it's oriented this way, and then it will fit. Again, it's the same in the quantum world. They did lots of experiments and quantum physics, the theory about quantum physics and the experiments to prove that it actually exists, they go back 100 years. So we did many experiments already, and you can watch YouTube for weeks on those experiments, and they actually work, and we know that it exists. On the right-hand side, we have entanglement, which is even more weird, where we can have, for example, two electrons with a spin in superposition that are entangled, which means they influence each other. When you observe one of them, it will collapse to one of its distinct states, and the other one that's entangled with it will collapse at the exact same moment in time to the opposite state. And when I say the exact same moment in time, I literally mean the exact same moment in time, which is something that scientists today still have no idea how that works. They have done experiments also. They have done experiments at space scale where they have a satellite orbiting Earth and they use two laser beams to transport two entangled photons, one to a lab in China, another one to a lab in Austria, and they measure and they look at them and they both collapse at the exact same time without any difference in time. So it's not possible, so they cannot be communicating to each other. So for some reason, they are entangled, as we say. Some scientists think that there's wormholes in between, but they basically just don't know. That's why they do. That's why they talk sci-fi shit. I don't know. Now, of course, these things exist. We have proven due to experiments or thanks to experiments that they actually exist. So we try to leverage them and build computers that leverage those specific properties and hopefully make computers more powerful that way. I will come back to why they are more powerful in just a couple of minutes. Now, the application is very clear to us today because there's a lot of talk about this. Tim already mentioned security very shortly in his presentation. The security we use today, like public-private key encryption, is basically built on the fact that classical computers are too slow to solve that. If you dumb it down, you basically have two very large prime numbers, which are your private key, the two separate prime numbers are your private key, and if you multiply them together, you have an even larger number, and this larger number is your public key. So the public key you can share with everyone, but somebody that has the public key cannot derive the private key from that, because you cannot factorize that very large number back into its original prime factors. Or you can, in theory you can, and if you build a brute force algorithm to do that, your computer will take thousands of years to solve that problem. So that is a problem that we created ourselves in order to have something secure. Now, of course, we also want to break these kinds of problems, or at least hackers want to do that. And quantum computers can maybe help them achieve that. Actually, the algorithm to break prime factorization already exists since the 90s. So the algorithm is there. The quantum algorithm is there. We just don't have the physical hardware that supports it yet, hopefully. Then, of course, things like drug development. A lot of things that we do, like, for example, drug development is something very complicated, because when you introduce a drug to the human body, it interacts with the human body and tries to solve an illness doing that. But the human body is extremely complex, and we basically exist out of trillions of very small quantum particles, and we need to simulate the interaction between those particles and between the drugs in order to know what is going to happen. But we have no powerful enough computer systems that can run those simulations. So we cannot basically do that. And that's the reason why we still do animal testing. We create a drug, test it on an animal like a rat dies, too bad, let's go back to the drawing board. If we had these systems that could fully simulate what's going on, then we don't need to kill animals to do that. One example. And very, very popular these days, AI and machine learning. In order to build the models for machine learning and for AI, we need a lot of processing power, because there's so much data that we need to process in order to build these reliable machine learning models. Again, when we can have an exponentially increased computing power, we can build better models. We can train better models for our AI, of course. I skipped the communication one. Communication is basically, we can also use quantum to do communication, because the cool thing about quantum is that when you have superposition and somebody observes superposition, the superposition collapses. And that is something we could actually use in communication, because when I send secret data to one of you, and somebody intervenes and listens on the channel, in quantum, in theory, we could actually see that somebody intervened, and we know, okay, somebody has seen what we are talking about. So you can, for example, when sharing passwords, you can invalidate the password when you see that somebody looked at the password in between the communication, which is a cool plus you have from quantum. So before we dive into actual code, let's very quickly explain to you what quantum looks like on a technical level. We all know classical computers because we are developers, right? Classical computers work with binary data, zeros and ones, two distinct states. We can combine these two distinct states to represent data. If we want to represent video or images, we just have something that we decided what a video or an image looks like, but it's basically ones and zeros in series. Now, in the quantum world, we can do exactly the same thing. We can still use the computing knowledge we have today. We still have two distinct states. For example, the spin of that electron, up or down, two distinct binary states. So we basically note them down as, again, 0 and 1, but we use the Dirac notation, as we say. This basically allows us to know this is a quantum state instead of just a classical state. Now, again, we can combine a quantum state into a more complex state, combined state, and this uses the same Dirac notation to tell us that this is a combined quantum state. Now, where things become interesting is that when we look at superposition, it actually allows us for that third kind of state. So not the distinct 0 or 1 state, but now we have a combined state of 0 and 1, as in 0 and 1 at the same time. Now, the idea of superposition is that when you observe this superposition, it will collapse to either 0 or 1, to one of its distinct states. Now, the alpha and beta values here, they represent the probability of that superposition state collapsing to either 0 or 1. And that probability can be 50-50, but we can also shift that probability so that there's a higher probability of collapsing to 1 and a lower probability of collapsing to 0, which is something very interesting and which is something that is being used in quantum algorithms to basically shift the solution to our problem into our advantage. That's the idea. You can, a cool example that I can think of is, for example, the Fourier transform, which is something that we can use today, where if you look at audio waves, for example. When you look at audio waves, when you have a band playing with multiple instruments, it's basically a combined wave of sound that hits your ear, and all together, this one wave sounds like all of the instruments together. Now, you can single out one single instrument if you want, or the lyrics, for example, or the person singing, by lowering the probabilities of all the other waves and higher the probability of only the singing voice. This is something we can already do today. And in the quantum world, it's the same thing, because this superposition state is also represented as a wave. They call this the wave function. And this wave function, we can also change these probabilities into in our advantage, basically. Now, there's a couple of rules here, because those are probability values. I'm not going to go too deep into this, but basically, if you square the absolute values of both, the result needs to equal 1, which is logical because the result needs to be 100%. So you just have a linear combination between those two values, and the result needs to be 1. The reason you need to take the absolute values is because alpha and beta are complex numbers. So if you were thinking about that, yeah, that's because when mathematicians see something and they don't have the numbers for it, they invent new numbers. And that's exactly what's happening here. So in order to represent the actual quantum state that works in real life, they need to use complex numbers in order to basically put that down in this linear combination, as you can see here. Now, you can also put this in a three-dimensional vector space from linear algebra, basically. If you look at a quantum state, you can see a sphere. This sphere is the vector space where this vector lives. It always originates in the center of the sphere. The length of the vector is always 1, the 100%. And you have 3 axes, x, y, and z. On the z-axis, if the vector points all the way up, straight up, that's going to be the 0 state, the distinct 0 state. If the vector points all the way down, that's the distinct 1 state. So those are those 2 states. All of the other infinite possibilities that this vector can point on the surface of the sphere is a kind of superposition state. And the reason I want to show this is because I think for a single qubit superposition state, it's very clear to me. If you look at the vector, psi on the right-hand side, it points somewhere to the top, and the probability of it collapsing to 0 is lower or higher than collapsing to 1. So if 0 is on top and 1 is on the bottom, is the probability to collapsing to 0 higher or lower? Higher, because it's closer, right? So for me, that's very clear. So in this case, indeed, the alpha value is higher than the beta value because the vector points more up. If that vector is somewhere around the plane on the x and the y axis, it's a perfect 50-50 superposition. And that's the reason why it's a plane and not just a single line, because it's complex numbers, so it can be somewhere on that plane. Okay, enough mathematics, or a little more, but let's... No. I just wanted to say, when I looked into quantum computing myself the first time, I bought a book. I opened the book, it was all mathematics. Started bleeding from the ears a little bit, but actually, when you really look into it, it's just basic high school math. So it's not that difficult. You know complex numbers, you know your basic linear algebra, and in this case, it's the same thing. If you dumb it down and if you say, okay, let's forget about complex numbers, let's just use real numbers, you have circles instead of spheres. And if you want to calculate probabilities on your vector, it's just trigonometry. It's just sines and cosines, and we all worked with that when we were going to high school, so it's actually pretty simple to debug your quantum algorithms by using the basic math you get from school. And now finally I have something that explains why math is important. I wished my professor told me many years ago, then I would have been more interested. All right, the reason quantum computers are more powerful is because of this superposition state. Now, if you look at, I told you about one qubit being in superposition, being a combined state, a superposition state. Now, if you combine two qubits together, these two qubits can potentially represent 4 different states. It's just binary logic. You have 0, 0, 0, 1, 1, 0, and 1, 1. But if you put these two qubits in superposition together as a combined superposition state, now you have 4 of these values at the same time. So my quantum computer can now represent these 4 states at the same time with only one calculation. So it's like doing stuff in parallel, basically. And the cool thing here is by only adding one single qubit, you double the power of your system. So purely theoretically, if you look at a quantum computer and a quantum CPU, or a QPU as they call it, a quantum processing unit, let's say if it has 100 qubits available today, in order to double the power of that quantum computer, you only need to add one single qubit, 101 qubits. If you look at a classical computer, a classical CPU, having billions or even trillions of transistors, in order to double the power of that CPU, you need to double the amount of transistors. So this is where they hope that quantum computers can be very powerful because we only need to add one single qubit in order to make that system or that quantum computer twice as powerful. Unfortunately, today we are still looking at what the best way of building a quantum computer is, because that's not easy, because adding one single qubit to a current physical quantum computer makes it exponentially more unstable, unfortunately. So scientists, and I know there's a lot of universities and companies in the Netherlands also looking into quantum computing, in Belgium also, all over the world, basically. They're all trying out different kinds of quantum objects that can represent qubits. For example, IBM is using superconducting qubits, which are basically electrons that they can change with microwaves. I know other companies like IonQ or Quantinuum, they are using ions and they change the state of the ions using lasers. So companies are just throwing shit at the wall and see what sticks, basically. But still a lot of things need to happen. We have actual quantum computers available today, but they have a small amount of qubits. Like in 2018, we had computer systems with 5 and 10 and 15 qubits. Today, we have systems with 50 to 100 qubits. Depending on the stability, it can even be more qubits. But we are still looking for more stable quantum computers. Now, if you look at quantum programming, an algorithm looks a little bit like this. The reason it looks like this is if you go back to classical computing in its early days, it was gates and circuits. In quantum computing today, we are at that level, gates and circuits. We have bits or qubits. We put them through gates on a classical computer that can be things like an exclusive OR gate or an AND gate or a NOT gate. In quantum computing, we have gates, but they are a little bit different. In this case, we have the H gate or the Hadamard gate, which puts a qubit in superposition or pulls it out of superposition. We have controlled NOT gates, we have X and Z gates, and we have measurement gates, for example. This is a teleportation circuit, it's a very popular one. This can teleport a complex quantum state from one qubit to another qubit. This is very interesting because in quantum, you can never copy a state. In the quantum world, quantum computing, quantum physics, you can never copy a quantum state. So that vector in that 3-dimensional sphere, that state can only be recreated by putting your qubit through the same operations up until that point that it reaches that specific state. But the things we can do in quantum is actually teleportation. We can teleport the state from one qubit to another qubit, destroying the original qubit. So the value is not copied, the value is teleported. Think about sci-fi movies. If I teleport myself from this spot to the other side of the stage, the original me will be destroyed, and there's a new me at the other end of the stage, which sounds a little bit painful. But it actually works, and the circuit is very simple. With that, I will shut up about theoretics, and I will now open Visual Studio Code, where I have installed the Microsoft Quantum Development Kit, which is just an extension to Visual Studio Code that allows you to write quantum algorithms using the Q# language from Microsoft. I only have 15 to 20 minutes left, so let's see if I'm a good programmer. I have a very bad mouse. Oh no, it works. Okay, so quantum programming language from Microsoft is called Q#, and when you install this extension, you can create a Q# application. Create a new project in Q#. You can also do this in Visual Studio. There's also an extension for Visual Studio, but I'm using Visual Studio Code today. Now, this seems quite familiar. We can create a standalone console application. Sounds weird in the quantum world, but the idea with the Quantum Development Kit is that when you run it on your local machine, you are simulating a quantum computer, which means you can only use a very limited amount of qubits, depending on how much memory you have. Because in the real life, a quantum object is quantum, so we can just encode whatever we program within that quantum object. It supports superposition. On a classical computer, we need to simulate this using the math that I just showed you. So when we have these multiple qubits that are in superposition together, the combined superposition state, we basically need to store all the linear algebra in memory. And when we add one single qubit, we need double the amount of memory. So my computer has 64 gigs of memory, which allows me to allocate 28 qubits. If I want to have 29 qubits, I need 128 gigabytes of memory. So you can also build quantum applications for specific hardware backends. This uses Azure Quantum. So you can build for IonQ and Quantinuum, which are now two supported external vendors that Microsoft is working together with, and we can build algorithms and run them on their physical hardware, their physical quantum computers, by sending our code to Azure, and then Azure will run our code on those backend quantum processing units. So for this, I will just do a simulation. So I'm going to use the standard console application. By the way, the simulation runs in a .NET application. So it's a .NET application that simulates the quantum application. So let's put it somewhere on disk, on my classical disk, not a quantum disk. I'm going to put this in this folder and call it the CHSH game. Now, maybe before writing code, I need to explain what this game is about. And before I explain what this game is about, this is what Q# looks like. It's a bit of a combination of languages you probably already know. Looks a bit C#-y, looks a bit F#-y. It's a combination. So you can see stuff like namespaces. We know what namespaces are. It's the same thing. You see open instead of using. We are opening or using existing namespaces. Microsoft already has multiple namespaces in packages that you can use for your quantum algorithm. Stuff that does machine learning stuff that does chemics-related stuff. You can just add NuGet packages, open the namespace, just like we know today, but in the quantum world. And then we have operations or methods. Now, what am I going to build? I'm going to build the CHSH game. This is a game. This is an algorithm that's pretty useless. The only usefulness, the only thing that is useful for the CHSH game is to prove that a quantum algorithm can actually outperform a classical algorithm. So we have a theoretical game where two people will play this game, Alice and Bob, A and B, and they get a random bit X and Y. So Alice and Bob, they play the game together, and each of them gets a random bit, 0 or 1. They don't know which bit the other one receives, because they can't speak to each other. That's the vertical line in between. I'm very good at graphics, by the way. So the vertical line is a wall, and they can't talk to each other. Now, based on this input qubit, the X or Y, Alice and Bob need to output another bit, A or B, and then the following formula will be calculated. X times Y needs to be equal to A exclusive or B. And when these two numbers are the same, they win the game. That's the idea. Very simple concept. Again, they get two inputs, X and Y. Alice gets X, Bob gets Y. Then they output A and B, and they can't communicate to each other. So because they can't communicate to each other, they have no idea what the other one is going to output. And they also don't know what the other one has as input. So basically, they have no idea what they're doing, like all quantum scientists. Now, if you look at some truth tables, you can see that if x and y equals 0, 0, or 0, 1, or 1, 0, that the result of the left-hand side of the expression equals 0, 0, 0, or 1. If you look at the right side, that's the right-hand side of the expression. If the output equals 0, 0, or 0, 1, or 1, 0, and so on, the right-hand side of the expression exclusive OR will be 0, 1, 1, 0. So the only thing that Alice and Bob can actually do is beforehand, before playing the game, just say, if we just both output 0 all the time, we have 75% chance of winning this game. Because when they both just output 0, the result of the right-hand side of the expression is 0. And the left-hand side, they don't know what happens because it's random. But it's random, and the result will be 0 3 times out of 4. So that's why when they just output 0, both of them, they will have a 75% chance of winning the game. Now, this is something we can already implement in our little solution here. So this is just a classical algorithm part, but you can also do classical stuff in Q#. So let's say we play this game a number of times because we want to play it multiple times so we can have a percentage there. So let's say let number of games equal 10,000. And now let's play this game classically and keep track of the amount of times we actually win. So I'm going to create a variable that is mutable, and this is going to be wins equals 0. Thank you, Copilot. I'm just going to call it classical wins. And now I'm going to do a loop for game in 1 till number of games. So I'm playing the game 10,000 times, and I'm going to define the input values. Yeah, this doesn't really make sense. So I'm just going to ignore this. But I'm going to specify those two input values. So let x equals get random bit. Get random bit is going to be a method or an operation that I will implement right now. So something like this. I'm going to return a Boolean. And this is actually the old notation for Q#. In Q#, you also do using when you define qubits. So yeah, I was talking about the fact that I'm now doing a classical algorithm, but I'm still going to use a qubit. Why? A qubit is perfect for generating random numbers. If we generate random numbers on a classical computer, it's always pseudo-random because a deterministic classical computer cannot do random. He has no idea what random is. We basically define a mathematical function that generates random numbers for us. But a quantum bit, if you put it in superposition and observe it, it will collapse to either one of its distinct states, 50-50. So that is really, really random. The hardware is already available today. You can buy a quantum device, plug it in USB, and it will just spit out random zeros and ones for you in a stream of data. That's not a joke, that actually exists. So I'm going to create a qubit, or allocate a qubit, as we call that, by using the use statement. Just like in C#, when we use a qubit, we need to dispose of the qubit when we go out of scope, so that another piece of the system can reuse the same qubit. You put that qubit through a Hadamard gate in order to put it into superposition. And then you can measure it, and then it will be 50-50% 0 or 1. So I can do return a measurement of my qubit equals 1. The result of a measurement is like an enum containing 1 and 0. It's not a Boolean, it's a result. I don't know why they did that, just to annoy me, I guess. So I'm just casting the result into a Boolean, basically. All right, next step is I need to play the game and output the A and B values. So I'm going to do let the tuple of A and B be equal to play classical game for X and Y. Thank you. I'm going to implement this function, and as I told you, when we play this game classically, thank you, I will return 0, 0, so false, false, all the time. Then we have 75% of winning the game, chance of winning the game. Now I need to calculate that weird expression that says the bit product. And now, again, this is the language itself has a little bit of a downside where you have to cast a lot of stuff because it's a type-safe language. So I'm going to add a couple of namespaces here, 1, 2, 3. I'm going to add convert because I need to convert in between types. I'm going to add math because I need pi at some point, and measurement because I need to do measurements, which is basically this one, m reset z. I will explain what m reset z means in just a moment. So the bit product will just be the x times y. But x and y are booleans, and I want to multiply them as integers, so I need to do something like bool array to int for an array containing only x. And I need to multiply this with bool array to int y. Now the other side of the expression is the bit exclusive OR. It is how you do an exclusive OR. You can do, for example, modulus of the a value plus the b value divided by 2. So it's the remainder after division of 2. So this is the exclusive OR. Now, if those two are equal, we win the game. If they are not equal, we lose the game. So we can do set classical wins, thank you, equals. So the classical wins, we increase that with 1 if bit product equals bit XOR. Otherwise, we increase it by 0. I don't want to write the if-else statement, so that's why I do it this way. Now, finally, I can just message the result. Message is like a console write line, and we even have string interpolation here. That is one option, but I want to do percentages, so let's change this a little bit. So classical wins divided by number of games times 100. Now, the types all need to be the same. So classical wins is a double, number of games is an integer, so I need to do int as double. Like this, and I'm going to round it in order to have just whole numbers. So round everything. Like this. And that's it. Let's run this already and see if we indeed have 75%. So this is chsh .NET run. As I told you, it's a .NET application that has a simulator running inside, and this will run my Q#. It will compile and run my Q# code. So please, computer, be quicker. I can drink. Ooh, that doesn't look good. It's not bool array to int, it's bool array as int. I'm sorry. Yeah, there's no IntelliSense here. Sometimes it works, sometimes it doesn't work. The IntelliSense. Actually, in Visual Studio, it works a little bit better. Please, help me. There we go, 75%. That's just a classical algorithm, right? Now, if you are prone to nosebleeds, please leave the room. Now, we can replay this game in a quantum world where we give Alice and Bob a qubit, but not just any qubit. We are going to give them an entangled qubit. They can't talk to each other, but when each of them has one of the pair of an entangled qubit pair, that entangled qubit pair can influence each other without communication, and we can do some very smart stuff with that. So Alice and Bob have a qubit. Those two qubits are entangled, and they still can't talk to each other. Now, in the quantum world, when we do an observation or a measurement, we do this in a kind of a base situation. So when I talk about we measure a qubit, and that qubit can collapse to either 0 or 1, we call that the value base, because it can collapse to 0 or 1. There's other bases. We can change those bases. We can also have minus or we can also have negative or positive superposition if we want to measure in another base. And that basically looks a little bit like this. So now we can just do very smart stuff, and this is why I want to show this algorithm, because quantum is basically finding something cool and smart that can help us to solve these kinds of problems. So on the left-hand side, you can see that Alice, she will actually measure her qubit in 2 bases. Or she measures in the value base, being either 1 or 0, or she measures in the sign base, being either plus or minus. That's 2 things we can do in Q# very easily. I will show you. Now, when she measures her qubit, the other qubit will collapse, and in quantum computing, it's not the opposite state, it's the exact same state. And Bob will measure in another base even. Bob will measure in a base called minus pi over 8 on the left-hand side, or positive pi over 8 on the right-hand side. And the reason for that is, if you look at that, you can see that these shifts in bases, they are actually closer to the state of Alice. So when Bob does a measurement, the vector will actually collapse depending on what Alice already measured, and thus influencing, not really influencing, but thus having an advantage and being able to predict. Now, I don't have time to go into a lot of detail here, but basically when you do the calculations, and I told you high school math, don't be afraid, you can already see here probabilities of 85% instead of 75%. So let's just implement whatever I'm showing you here. So I'm going to play this game in a quantum way. So I'm just going to copy paste. I'm not going to try to be smart about this. Just going to copy paste everything. I'm going to call this quantum wins. I'm going to call this quantum wins, and this also quantum wins. This also, and this. When you start copy pasting, you make mistakes, right? This should also be quantum. So this plays the exact same game as before, but now we're going to implement the play quantum game function or operation. And we see if the result is different. So play quantum game. What the hell? Quantum. So if we actually play the quantum game, we are going to output that A and B value from the graphic, right? So A and B were the output values. So I'm already going to create a mutable variable or tuple containing A and B, which will be false and false. And this is what I want to output. Now, I need to create those 2 qubits, one for Alice, one for Bob. So I can use a tuple of qubits, one for Alice, one for Bob, equals a tuple containing 2 qubits. By the way, the reason qubit is not like new qubit, but it's qubit and then some, whatever that's called in English, it's because it's a factory function. It's a factory function that returns to you a qubit that's being allocated for you. Now, in order to put a qubit in superposition, we already know that's the Hadamard gate, H4QA, for Alice's qubit in superposition. In order to entangle 2 qubits together, very easy. If one qubit is in superposition, we just need to add a C-NOT or a controlled NOT gate that, depending on the state of the first qubit, flips the second qubit around the x-axis. So when qubit A equals 0, nothing happens to qubit B. When qubit A equals 1, qubit B will be flipped around the x-axis. So when qubit B points all the way up on the z-axis, if we flip it around the x-axis, it's just like a NOT gate. It flips it from 0 to 1 or from 1 to 0. But if qubit A is in superposition, it's 1 and 0 at the same time. So qubit B only flips when qubit A is 1, but it's 1 and 0 at the same time. And that's why the 2 are now entangled. That's the only thing you need to do in quantum computing algorithms to make 2 qubits entangled. So, done. Now begins the interesting stuff. So Alice needs to measure her qubit in the value or sign basis, right? So if X is something, else something else. So let's implement. Yeah, I'm just using Copilot to help me do all of the curly braces and stuff, but the things that it's creating, they somewhat make sense, but not entirely. So in order to calculate on the value basis, we need to do a z measurement. A z measurement because we're measuring on the z-axis, 0 or 1. That's the idea. So I'm going to do set A, so I'm setting the result of A to a measurement on the z-axis of qubit A, and when that equals 1, we're good to go. If you want to measure on the sign basis, you need to measure a different axis, which is the x-axis, because the x-axis lies on that plane in that sphere. So when you measure there, you basically measure that plus and minus superposition state. So that's that. Now we have A, and now we do the same thing for Bob. So Bob also needs to do his measurement, and he has a little weird thing that he needs to do. He needs to basically in Q# you can only measure on those 3 bases, X, Y, Z. But in the quantum world you can measure on whatever basis you define yourself. But what we can do in Q# is we can rotate our vector in that 3-dimensional vector space. And we can rotate using the Ry or Rx or Rz. We can rotate an amount of degrees in radians around a specific axis. So I told you, Bob needs to rotate pi over 8 radians or minus pi over 8. So in this case, he needs to rotate pi over, actually it's 4. It is 8, but you need to specify 4, and I can prove it to you if you look at the documentation, because the angle you specify here will be divided by 2. So pi over 4 divided by 2 is pi over 8. So yeah, documentation, people. So we rotate the Bob's qubit pi over 8 radians, and then we do a measurement, and we do the same thing in the other case. When the input y equals 0, we rotate minus pi. By the way, what I'm doing here, when y equals 1, we rotate pi over 8. When y equals 0, we rotate minus pi over 8. That's what happens here. So the circle on the left-hand side is Alice needs to measure in the value basis if x equals 0. The right-hand side needs to measure in the sign basis when x equals 1. And here it's the minus pi over 8 when y equals 0 and positive pi over 8 when y equals 1. That's what I'm doing right here. So if everything went fine, I can run this. Excuse me? Ben ik semicolons vergeten? Oh. You are my hero.
You're 10 minutes over time, just an answer.
Yeah, I'm sorry. I'm finished right about after this build error.
Did you measure
I measured using the M-reset Z. So this M-reset Z, you can measure by just doing M, which is by default the Z-axis. If you want to customize your measurement, you need to do M-reset Z or Y or X. And the fact that it also has a reset is because when you dispose of a qubit in Q#, you always need to reset it back to its original 0 position. That's the reason. And as you can see, in the classical winds, we have 75% as predicted, and in the quantum winds, we have 86 or 85% as we predicted, as we calculated by just using basic trigonometry. And I know this is a very stupid example. I just wanted to give you an idea of what Q# looks like and how you need to think in a very smart way in order to tackle these kinds of problems, in order to have a higher win chance for this specific example, but for other examples, just need to leverage the quantum world in a different way we would do in a classical world in order to have more power or better solutions to whatever problem we try to solve. And with this, I'm very sorry to be over time a little bit. Everything is, again, available on my GitHub. And if there's any more questions, I'll be here. I'll be walking around. By the way, I also did this in a book. During COVID, I told my wife to shut up. I'll be upstairs and writing this book. I'm not sure if I would ever do it again, but I had some fun. And if you are interested in my book, you can come and have a look. And after the conference, when all the sessions are over, if you come and find me on the main room there, come and talk to me. If you have any questions, you will get this book from me. So the first one that talks to me, because I have no friends, can have this book, right?